What's going on in the control room today?
We're making a nucleus go really fast and smash it against another one.
That's basically what nuclear physics is all about, isn't it?
It is. It's as I.
Have you guys grown up at all?
No, it's banging the lumps together and watching them fly apart.
Okay, what particular kinds of lumps are you looking at today?
Well, today one of the experiments we're doing is we're using an isotope of lithium, lithium-7,
Yep.
and we're bombarding it against different targets, one of which is gold.
Right.
So
lithium's quite small, right?
It is. It only has 7 nucleons. So
Yep.
what we're looking at is what happens when these two nuclei get very close.
Yep.
So in particular, we're looking at the lithium because it breaks up into different pieces as it gets near the target.
Even though it's small?
Even though it's
small. It breaks
small.
up into even smaller bits?
It does, it
Yeah.
does.
Why is that?
It's
Or is
because
that what you're trying to work out?
yes, it's the interactions between the different protons and neutrons within the nucleus.
Yeah.
So some configurations are more stable than others.
Yeah. What do you mean by configuration?
So you've heard of helium.
Yep.
Okay, so helium, normal helium-4 has 2 protons and 2 neutrons.
Yep.
And that's a particularly stable configuration.
I guess they kind of sit together in a kind of cross shape or
Yeah.
tetrahedron for the nerds out there.
I must admit I don't know exactly what
Yeah.
shape it is. But yes, so and that configuration of helium
Yeah.
is sort of part of what's in lithium. So
Right.
in lithium you have this helium nucleus or
Yeah.
cluster, and then you've got 2 more neutrons and a proton,
Yeah.
which sort of form its own group.
Ah, so you've kind of got 2 bits stuck together.
Yeah, so it's a cluster formation.
And they kind of break apart.
And it can break apart
Yeah.
through the forces when it gets near another nucleus.
Okay. But it sounds like it's not sure because you still need to study it.
Well, we're not sure exactly what the physics is of
Yeah.
when it breaks apart and what the influences are
Right.
that make it do certain things at certain...
What are some of the
Points.
influences that it might be?
Well, there's 2 main influences in nuclear reactions. One is the Coulomb force.
Mm-hmm.
So
So-
basically, 2 negative things don't want to get close to each other.
Mm-hmm.
Actually, it's 2 positive things don't want to get close to each
Positive
other.
nuclei, right? Yep.
Positive nuclei.
Yep.
So that's one of the forces.
So they kind of repel.
So they're they're not
Yep.
trying to get too close to each other.
Yeah.
And that's a long distance force.
Uh-huh.
And you've got a second force, which is the strong nuclear force.
Yep.
And that's a really short distance force, but that's attractive.
Right.
So if you can imagine 2 tennis balls with magnets in them and Velcro on the outside.
Right.
So you get them
Yep.
closer and closer and they don't want to go anywhere near each other,
Right.
but if you get them closer enough, the Velcro
The Velcro sticks.
sticks them
so
together.
Velcro is the strong nuclear force.
Sort of, yeah.
Okay, that's cool. I like that.
Yeah.
Yeah.
So,
So what we're doing here is you kind of throwing it and hope the magnetic force will break the lithium apart. Is
yes,
it-
so it's in that cluster
Yep.
formation in lithium is which gets influenced by the big target most. So, you know, is it the influence of the helium particle, or
Yep.
is it the influence of that proton with the 2 extra neutrons,
Ah, I see.
which wants to get closer to the target?
Right. So
More
one
than
might
the other.
kind of stick with the Velcro and the other bit fly off.
Yeah.
So you're collecting the bits to see.
So we're basically looking at the bits that fly off.
Right.
We're looking at low energies, so that Velcro, we have to, you know, only just that Velcro touches.
Right, okay. Okay.
So we eliminate.
So what do you call low energies here? What's your voltage?
Well, at the moment we're looking at 36 mega electron volts.
Right.
So-
36 million electron volts. So that's around about what? 10 million car batteries? 30 million car batteries?
I must admit, yeah, I don't
Well,
know.
they're about,
But yeah,
they're
yeah.
about 14
Yeah.
volts, aren't they?
So-
yeah, so that's low energy for you guys.
Well, it's low energy because we have to give them a certain amount of energy or they're just not going to fuse.
Right. So basically the gold is just a thing to bounce off. You don't really break the gold up.
Part of the problem is if it was classical, so if you had a bowling ball and a billiard ball,
Yeah.
that's what we call classical physics.
Yeah.
But here we're talking about quantum physics. So in quantum
Yeah.
physics, the bowling ball would be able to overlap with the the cue ball or whatever
Yep.
you have. So quantum physics is a bit different.
Right, okay.
So even though we're below that classical barrier, things still happen.
Oh, okay. So there's a bit of quantum tunnelling.
Yes,
They
quantum
kind of
tunneling going
Get
through.
tangled in each other and... Okay.
So we're down in that sort of region.
Right. Sounds very complicated to work out which bit is which.
Well, there's a few pieces flying out, but we've got detectors which will detect position, so
Right.
where things are when they fly out,
Yep.
and how much time it takes for them to fly out to that position, and what the energy they have when they get there.
Right.
And from that, we can reconstruct what actually it was. So we have a beam from the accelerator come in from the left. It hits a target in the middle of the detector.
That looks like it's not straight on.
It's at 45 degrees.
Uh-huh.
We then have a reaction. Then we see the products of that reaction in those large area detectors, the 3 of them that are around the outside.
So the sort of dark coloured things that are vertical
Yes,
around it.
Yes. And they've got wires in there so we can see the position of where the particles hit.
So once you have a good handle on what's happening with the bits flying apart, where to next? How does that help the bigger picture?
Well, what we're trying to understand is how nuclei interact with each other.
Yep.
So why would we want to do that? Well, there's a number of reasons. One is all about where on earth do we come from in the first place? So most elements are produced in stars or in the cosmos, and that's all through nuclear reactions. So we can understand more about why there's certain abundances of certain elements on Earth by understanding how the cosmos produced them all in the first place through nuclear reaction.
So that's hydrogen fusing to form helium, fusing to form bigger things, the lithium right
Yes.
up to iron in our
And
blood.
there's different processes that happen there.
Yep.
So some of them are just sort of fusion, some of them, you know, a nucleus might absorb lots of neutrons through some fast process and then form a new nucleus and then decay away and then get some more neutrons and then split into 2 other pieces. There's a whole range of reactions that
This
can
is
go
all what's
on there.
going on in a star.
Yeah.
Right. We don't fully understand those right now then. from what you're
No,
saying.
no. So we're still trying to work out exactly what are the conditions needed for some of those reactions to occur, and what are the reactions that are actually occurring.
I guess the bigger the thing that you've formed, the more ways it can break apart, different combinations and permutations and so on.
Yeah, so certain nuclei will be more prone to, say, absorb other particles or to fuse than other nuclei.
Very complicated mess inside a star. And you simplify it inside the accelerator here.
We do, we do. But even closer to home, it's very useful knowing about nuclear fusion and fission. Last month, I had to have a bone scan of my leg.
Right.
And that happened because I was injected with a radioactive medicine, which had a nuclei called technetium-99.
Yep.
And that's produced through a nuclear reaction. It's through fission.
Yep.
And that's really useful because it has a really short half-life. The body doesn't use technetium, so it can just get rid of it.
Yep.
And it's the radiation that it produces is fairly long distance, so it doesn't sort of cause local problems.
Right.
So, and you know, half of it's gone in 6 hours. So.
Right. But for that 6 hours, you were emitting gamma rays from your leg.
Well, from my whole body.
From your whole body, yes.
Yes,
Okay.
it was just
Right.
my leg happened to be where they were looking. So.
Yeah, okay.
Oh, my leg's fine, by the way.
Oh, good. Happy to hear that. All right, thanks very much, Annette.
No worries, thanks.